All right. Thanks, everyone. So today we have Alex Clark from the University of Bristol. We'll be talking about hybrid quantum technologies. Take it away.
Excellent. Thank you very much, Ravi. It's really a pleasure to be here. It's been an absolute whirlwind tour of the kind of America so far, of the US. Been in Boulder this week, visiting a bunch of companies and NIST, and then Quantum 2.0 yesterday, Stanford this morning. So excuse me if I'm tired, but I'm really excited to be here. So I'm excited to tell you about the research that happens at the University of Bristol in the Quantum Engineering Technology Labs, which I'm currently the director of. I've titled this Hybrid Quantum Photonic Technologies. A lot of the technologies we work on in the Quantum Engineering Technology Labs center around photons and quantum optics. I'm going to specifically tell you about this molecule later, which I use to generate single photons and coherent photons at low temperature. But first off, I'd like to tell you a little bit about Bristol, because I'm not sure all of you will know where Bristol is. Let me just click this once, and hopefully that allows me to do this. Very good. So many of you will have been to the UK, but maybe you've only been around the London area. We're off to the west here, just near Wales. So Bristol is what we call the capital of the West. It may look a long way on here, but as you well may know, the UK is quite small, so this is actually only a 1 hour train. So if you do come to London and you want to come and see what we're up to in Bristol in the labs, then drop me an email. You're all very welcome to visit. Something that Bristol is quite famous for, and you'd get to see if you come to visit, is this suspension bridge that crosses the Clifton Gorge. This was designed and built by Isambard Kingdom Brunel, one of the original bridge builders, who also built the first boat that crossed the Atlantic, the first steamboat. So you can come and see those in Bristol. They have this Great Britain and this bridge, and we'd be very welcome. The university is around 30,000 students, 8,000 staff, 3 different faculties. We're in the science and engineering faculty. And we're ranked 5th in the UK for research output and excellence. So we're really a research intensive university. This is just a bird's eye view of Bristol, just showing some of the quantum activities that are happening across the campus. So the physics building is right on top of the hill, and if this works, is a kind of drone shot of our building. So we have this nice kind of castle-looking building. This is the top of one of the lecture theatres. We're actually a city centre kind of campus. So we're right in the city, but we have some nice green areas around. And this is a clean room down here and a part of the physics building over here. We have 6 areas of research in the physics building, spanning kind of theory, experiment, particle physics, astrophysics, and I'm in the quantum engineering technologies team. The quantum engineering technology labs are housed in the nanoscience and quantum information building next to physics. This building was originally built and embedded into the bedrock of Clifton, the area, to get a very low vibration building. It was one of the quietest buildings in Europe for a while. I don't know if we still hold that record. But then we also float lots of concrete pads in the basement of the building, one of which houses a Wraith Voyager e-beam system. It's okay. You got it? Cool. Wraith Voyager e-beam system, which we use to make nanophotonic structures down to kind of 50 nanometer resolution. Lots of material deposition, reactive ion etching, and laser writing in the clean room that connects the 2 buildings, where we can make nanophotonic structures as well. In the top floor of this building, we have 16 dedicated photonic characterization setups in kind of one big room, lots and lots of shared equipment so that people can characterize their photonic devices, and then a shared facility that's connected around the whole university by telecommunication band optical fiber that has access to 48 superconducting nanowire single photon detectors from various different companies. At the moment, I think we have 2 photon spot systems and 1 single quantum system. But this is fully reconfigurable, software defined, so that the students at the start of the week all argue about who's going to get which detectors, and then they redefine the switches in the telecom rack, and they're all able to run their experiments and remotely dial into the Swabian time taggers that check when photons have arrived at each detector. We also, and one of the reasons I'm here in the US, have 2 centers for doctoral training. These are kind of graduate schools that also allow us to hire in PhD students. They take on about 10 PhD students per year. The new one is called the Quantum Information Science and Technology, CDT. This is joint with the University of Sussex. There's about 8 students in each site. Each year, the students do graduate courses before they choose their PhD project, and they also get to go on an industry trip, and that's why we're here in the US. They're at the moment on the industry trip, and they're at SciQuantum today. So I got to come here, and they got probably a really good lunch. And so overall, we've had this quantum engineering center for doctoral training for 10 years, and this one's got 5 years to run. And we trained over 100 PhD students in quantum technologies as these things have run. Something we're also quite proud of is our entrepreneurship schemes in Bristol. So we have something called the Quantum Technologies Enterprise Centre, QTech. This was an entrepreneurship training program where postdocs came in with nascent ideas around quantum technology products they wanted to generate, or ideas around what kind of company they might want to form. And they were trained in entrepreneurship, business planning, got introductions to investors, how to pitch, all these kind of things. And this resulted in Bristol being the home to 1/3 of the UK quantum startups, although some of them have now got bigger and moved to other places as well. So yeah, quite proud of that. And we're just building a new campus down by the station that's going to house the Quantum Technology Innovation Centre, where companies can come and collaborate with academics. And we can also have that kind of incubation space that small companies need to be able to grow. Overall, we have 10 group leaders in quantum technologies in the quantum engineering technology labs. There's my group, so I work on, you'll see, molecules as photon sources, but also nonlinear quantum sensing and imaging schemes, LiDAR systems, and quantum memories based on cold and warm rubidium atoms. Anthony Lang's group works on integrated photonics for quantum simulation and quantum computing, and now also has a spin-out company called Duality Quantum Photonics. John Rarity is kind of a pioneer of quantum optics in the UK, worked on some of the early days of interference experiments back in the 1980s, and has been working on quantum communication and imaging and many other things since, and still holds a presence at the university, although he's semi-retired. But we still keep him around because he's a useful person to ask questions to. There are 3 groups who are working on quantum dots, Ruth Alton's group, Andrew Young's group, and Edmund Harville's group. Edmund also works on vertically emitting lasers, especially ones that are compatible with quantum technology development. Andrew and Ruth work mainly on coupling quantum dots to nanophotonic structures to increase the extraction efficiency of photons, but they also work on spin-photon interfaces and using the quantum dot in a nanophotonic structure as a nonlinear optical element. Krishna Balram's group works on microwave to optical conversion schemes using integrated gallium arsenide nanostructures, so suspended gallium arsenide that can interface with acoustic modes, optical modes, and also our piezoelectric, so can launch microwaves as those acoustic modes. And then Siddharth Joshi works on quantum communication systems, entanglement distribution. He holds the record for distributing entanglement to 19 users simultaneously in a metropolitan network, and has more recently been working on space-based quantum key distribution systems. The quantum technology hub that he works in, or the Quantum Communication Technology Hub at the UK, they're launching a CUBE satellite in October this year called SPOC, and it's going to have a discrete variable and continuous variable light sources on the satellite that are going to be coming down to Earth while they orbit. So we have a mobile ground station in Bristol to be able to look up to that satellite, and there's a fixed ground station in Scotland. So the plan is to have a distribution of keys between Scotland and Bristol and elsewhere in Europe. Julia Rubino works at the intersection of kind of quantum foundational questions and integrated photonics. So at the moment, she's working on something called indefinite causal order, where you can perform quantum operations in a superposition of A, B, or B, A. And it turns out this has interest not only for our idea of what time is, but also whether quantum mechanics obeys these kind of commutations. And apparently this could also speed up quantum computers. But she always blows my mind every time I speak to her about this. So I haven't... I definitely don't fully understand why that would be the case. Carrie Widener is a new hire in Bristol. She's been in Bristol for a few years now, but Carrie works on cold atom systems, so quantum gas microscopes, to be able to control single atoms, control their interactions, but also works on what's called a shaken lattice interferometry. So by cooling atoms to VEC and dropping those into an optical lattice, if they experience a shift and you read out the momentum of the atoms, then you can use this as an inertial sensor. So she's working quite a lot on that in collaboration with Inflection. We're involved in 3 of the previous UK quantum technology hubs, one on computing and simulation, one on communications, and one on quantum imaging. And more recently, we've now joined 3 of the new quantum technology hubs. I guess I should praise what they are. A quantum technology hub in the UK is a large project that brings together somewhere between 10 and 15 universities, maybe about 40 academics, all working towards some common goals. In the case of this quantum sensing, imaging, and timing hub, kind of does what it says on the tin. Our contribution is to do gas sensing, which I'll tell you a bit about today. This quantum position, navigation, and timing hub carries inertial interferometric measurements, will be in that. And this integrated quantum networks hub plans to integrate quantum memories into quantum networks for large-scale entanglement distribution. Okay, that's probably enough about everybody else. I've tried to concentrate on what I do for the talk here today, and I hope to be able to tell you about 3 different experiments that we've been doing around different kinds of interference effects that we use to look at molecules. My group has, since moving back to Bristol from Imperial College, concentrated on molecular quantum photonics as the area of research. So we're interested in taking organic molecules, seeing how they interact with photons, with electrons. So seeing how, whether they can act coherently at various temperatures and under various conditions. We then couple those molecules to nanophotonic structures. If you have just a single molecule or any single defect, like a quantum dot atom or a defect in a crystal, it generally is going to emit into 4 pi steradians if it's in a homogeneous electromagnetic environment. And so to encourage emission into a well-known direction, we structure the electromagnetic environment by putting the molecule close to or inside optical waveguides and optical cavities so that we can always collect the photons from these systems. If I have a molecule that's well coupled to an optical waveguide, and then every time it decays into the propagating optical mode, I can turn that picture around and say, if I send a photon in that's resonant with the molecule and it's in the waveguide, it's going to interact with that molecule. So the whole picture can be time reversed. If I can do that, then I can tune the photon so it's close to resonance with the molecule, and it'll pick up a phase shift when it passes the molecule. So I can look at, say, single molecule sensing or single photon detection based on the single molecule if I can couple it into a nanophotonic interferometer. So this is another research direction that we have for these molecules on chips. Something that's quite close to my heart is nonlinear optics. My PhD was generating photon pairs in nonlinear optical fiber and then in nanophotonic structures. And I still work with nonlinear optics now, but mainly for imaging, sensing, and for frequency converting the emission, the photons emitted by molecules between the kind of near infrared region where they emit to the telecommunication region where we can send them over long distances. The molecules that I choose to work with, which you've seen a few times now, the main one we work with is called dibenzotyrrolene, and we chose that molecule because it has emission wavelengths that are close to the D1 and D2 lines of rubidium atoms, so around 780 and 795 nanometers. So that means that the photons that are emitted by the molecule can interact with rubidium atoms, and we can use the rubidium atoms to store the single photons that are generated by the molecule, and then we can read them out at a later time. So this will be an atomic quantum memory, and if you can have such a quantum memory and photons that are resonant with it, then you can extend the distance over which you can perform quantum communication and entanglement distribution. Finally, the molecules, they're very good at emitting photons, and they're very stable, and I'll show you that later. But unfortunately, the ground state in the molecule is a singlet state, so you don't have access to the spin of the electron in the molecule that you're using to generate the photons. However, the molecule does have a triplet excited state, and in this state, you can have access to the spin of the electron, although you're limited by the spontaneous decay of this state back to the ground state. Now, luckily, that's a spin flip transition, and so what that means is it's not allowed very much. So this is actually a long-lived state. It lives for about 10,000 times longer than this singlet excited state. So this lives for about a few nanoseconds, but this one can live for tens or even hundreds of microseconds. So you can still do quite a lot of operations on it, on the electron while it's in that excited state. Okay, I want to concentrate on these 3 different interference effects that we've used in order to perform molecular spectroscopy or to interrogate what's happening to molecules in the system. The first one is to actually use something called nonlinear interference to measure the concentration of gas molecules in one of the beams of a nonlinear interferometer. I will tell you how this works in a minute. The second case is going to be looking at two-photon quantum interference, so interference between two photons emitted by a molecule to assess the coherence of the molecule emission. And the third kind of interference that I want to talk about today is interference between laser light in an optical waveguide that passes a molecule and light that's scattered by the molecule. So it turns out if laser light comes into and passes a molecule, there's a probability in the low excitation regime that you'll just coherently scatter that light. You'll resonantly Rayleigh scatter that light back into the optical waveguide. And the light that's scattered by the molecule will pick up a phase shift compared to the transmitted laser light that went past. And if you have, I should also say that the light scattered by the molecule in this very low resonant Rayleigh scattered regime has the same line width and the same wavelength as the input laser. So now you have the same line width, same wavelength, but a phase shift. So these two fields will interfere with one another, and you'll see an interference effect at the output of the device. And the strength of that interference will tell you about the coupling efficiency of the molecule to the nanophotonic waveguide. So let's take a look first at this nonlinear interference case over here. So many of you will be familiar with a standard optical interferometer. So if I send in laser light into one input port of a beam splitter, the laser can be reflected or it can be transmitted through the device. If I then recombine those beams on another beam splitter and the arms are balanced, there's no phase shift in one arm of the interferometer, then the light will always come out at the bottom of this interferometer, for example. Now, if I apply a phase shift in one arm of the interferometer, then I'll shift some of the light to the other output port, and I can switch the light back and forth depending on how many radians of phase I apply in one arm of the interferometer. So this is a Mach-Zehnder interferometer, and it's a typical one that's used for sensing this phase. It operates usually with only one frequency of the laser. You can reach a shot noise sensitivity of measuring this phase in one arm of the interferometer, if that's what you're interested to do. You can do better if you apply squeezing in the interferometer. You can, of course, employ other configurations of such laser interferometers, like a Michelson type interferometer that they would use at LIGO, for example, to detect gravitational waves. And it's reasonably simple setup here, only two beam splitters, all passive kind of linear optics. But there's another type of interferometer that you could employ, and that's replacing these beam splitters with what we call parametric amplifiers. So parametric amplifier, in this case, you can think of it like a two-mode squeezer, or if you prefer to think of it as photon pair generation in a nonlinear crystal of some kind, then I'm able to pump one of these parametric amplifiers and generate correlated beams of light in each arm of the interferometer. If I recombine those beams of light that are generated on a second parametric amplifier, I have a very similar interferometer here. And the interference, the suppression or enhancement of the photon pair generation in the second crystal depends on the phase in one arm of the interferometer. So I can pick up interference fringes on either the bottom or side output, depending on the phase shift I apply in one arm of the interferometer. Now, the interesting thing here is I've drawn these with two different colors, and that's because I can usually pump with one particular color and I will generate photons. If this is spontaneous parametric down conversion, for example, I'll generate two lower energy photons whose energy sums to that of one photon from the pump. So this means I can actually have quite different colors in each arm of this interferometer, as different as having one of them in, say, the midwave infrared and one of them at a visible wavelength. Now, you can see if I apply a phase shift just to this one arm of the interferometer, the mid-infrared arm, I will get an oscillation, an interference effect in the output in both the blue and the red output here. That means by only applying a phase shift to the mid-infrared photons that are generated, I'm able to see an interference effect by detecting visible photons and throwing away all the mid-infrared at the output. So now I had some kind of, non-contact interaction, let's say. I have some non-contact sensing happening, where I can have sensing that's only happening in one wavelength while detecting the other wavelength. This is nice. It means that actually the noise is correlated between these two beams because they're correlated in their intensity. Similarly to the linear interferometer, this nonlinear interferometer can employ other configurations as well. And this has amplification built in. It's a parametric amplifier. So if you operate these at a high pump level, then you can avoid losses in the system as well. This is not a new idea. It's been done for quite some time. So back in the 1980s, Yerk, McCall, and Clowder demonstrated this kind of interferometer using four-wave mixing in warm atom vapors. So these are just vapor cells that contain rubidium, and they're doing four-wave mixing between the levels of the rubidium. And they were able to see that by applying a phase shift into each arm of this interferometer, they were able to see interference effects at the output. Few years later, Mandel's group, so Zhu, Wang, and Mandel, implemented a similar interferometer, but they used nonlinear optical crystals, like the ones I talked about in the last slide, in order to do parametric down conversion and pass one of those photons back through the nonlinear crystal here. And they were able to see interference effects as they shifted one of the beam splitters in to change the phase in the interferometer. A few years later, John Rarity, alongside Anton Zeilinger, Herzog, and Weinfurter, demonstrated a Michelson-type nonlinear interferometer. So here they pumped a nonlinear crystal, and instead of having another nonlinear crystal after that to have a Mach-Zehnder interferometer, they reflected all the beams that pumped signal and idler light all back through the nonlinear crystal. So you're using the same nonlinear crystal twice. But what happens then is, if you move, say, the idler mirror, then you can see when you detect just the signal photons on the output, that you can see this interference effect. Now, in these early days, all of the photons that they were generating were generally similar wavelengths to one another. So they didn't see this kind of wavelength diversity aspect of the sensing happening in one wavelength and the detection happening in the other. They were exploring the physics back in this time. So Anton Zeilinger found in 2004, or presented in 2014, what he called imaging without detection. In this setup, they used two nonlinear crystals, were able to generate very different colors of light, one of them being around 800 nanometers and one 1550 nanometers, so 1.5 micron, using a green pump laser. And they were able to show that putting an object into the telecom, the 1550, they were able to see the image formed only by detecting the visible output in the interferometer. So imaging without detection, because you don't need to detect the light that passed through the object. And you can be at very different wavelengths to one another. Over the next few years, this was taken and made kind of more compact and more compatible with applications. So this is a similar wavelength system where they pump with a green laser and generate 1550 and 800 nanometers. But now they're using it in a Michelson-type interferometer wrapped around a single PPLN crystal, a lithium niobate crystal that can generate these photon pairs. And they were using it in this case to look at voids underneath a silicon surface to look with a proposal that this would be good in assessing CMOS electronics with low light levels and high sensitivity. On the same year, Sven Ramalau's group showed that they could image biological structures, and here they were really extending the wavelength out. Here they had a 3 micron idler wavelength and an 850 nanometer signal wavelength, so they could still detect the signal with a CMOS camera, but they could see what was happening in the midwave infrared on biological samples. I think this is I can't remember if it's mouse lung or mouse brain, but it's a piece of a mouse. And able to show that this can work with biological samples as well. So this is quite nice technological development of using this kind of interferometer. So at Imperial College, when I was there before, I started working on this with a group of Rupert Alton and Chris Phillips. And we worked on making these systems more compact. The Zeilinger system took up a whole optical bench to be able to demonstrate this imaging without detection. And we've now got it down to something that's quite small, on the order of shoebox size. We've also been pushing the physics of these interferometers, introducing losses into each arm, optimizing the interference visibility, or optimizing the amount of photons that the sample sees, whether it wants to see fewer photons, but we can still detect what's happening. We've used the system for midwave infrared gas sensing, and I'll talk about this one in quite a bit more detail shortly. We also worked on the underlying physics of if you can seed the interferometer, as in you don't only input your pump wavelength, but you input your sensing wavelength. You can still use your visible light detection, even though you're using midwave infrared for seeding, but you can enhance things like the interference visibility or the coherence length of the photons that you're generating. So we took, like I say, an optical bench size experiment and shrunk it down onto something that was about half a meter by half a meter in size, so a couple of feet by a couple of feet. And we were using similar wavelengths to those that Zeilinger was using previously. So 532 nanometer pump, an easy green laser to work with, generating around 750 nanometers and between 1 and 2 microns in the ideal wavelength. Still using a standard CMOS camera, but this system costs, I guess this is the equivalent of around $10,000, but not including the laser in this case, which cost a bit more than that at this time. Still, this system was pretty robust. We took it out across London and took it to a showcase event to show it working in the wild. We even shipped it out here to San Francisco for Photonics West and demonstrated it on the show floor, showing that it could work. So showing that this thing is really portable and could be used as a mid-wave infrared microscope in another lab, for example. And then we were also able to take it actually to an art gallery where they were installing different quantum experiments next to pieces of art. So quite fun to get this outside of the lab. More recently, we've shrunk this down to an even smaller size, so it's now a shoebox size system, and we're using quite a cheap off-the-shelf laser. This is actually a laser that people generally use for like special effects, children's parties and things like this. So it turns out we can use a very cheap laser. So now the whole system is around, I guess that's $8,000, £6,000 or so. But really the expense now is just coming from the fact that we use Thor Labs components, which we should get rid of and use our own machine kind of aluminium, and then we really get even cheaper. So how does this system work? So I'll just show you that we imaged this is a interdigitated electrode structure that we imaged. We only chose to image this because I had it lying around in the lab, but it has pieces that are reflective, pieces that are absorbing, and there's polymer on the surface as well. So what do? You take a set of images in your interferometer, and you're scanning one mirror in the interferometer to vary the phase in the interferometer, and you're taking an image at each phase shift. After you've taken these images at each phase shift, then we perform a fast Fourier transform, pixel-wise, across the image, and we're able to pick out the contrast, phase, and visibility of the interference. And in doing so, we're able to clearly see the structure that we're imaging. Here, we're probing the structure at 1.5 microns, but we're only ever detecting the 810 nanometers using a standard CMOS camera. By changing the temperature of the nonlinear crystal and changing the polling period that we use, we're able to change the wavelengths that we're generating in the interferometer. So we go from 810 to 760 nanometers being detected, still easy to detect by a silicon camera, but now the probe is quite far out where it's quite difficult to detect light at 17, 18 nanometers. We've also taken this interferometer and introduced an object into one arm of the interferometer, but instead of having it fixed in position, we rotate the object around inside the infrared beam at different angles. We take an image or a reconstructed image at each angle, and using all of those angles and performing a radon transformation, like you would have in a CT scan in a hospital, we're able to reconstruct the full 3D object that we put into the one arm of the interferometer. So this is quite fun. We're doing kind of 3D imaging without detection, which is kind of neat. So this has just been put on the archive like earlier this year, and hoping it comes out soon. I mentioned earlier on that by seeding one arm of the interferometer, we can enhance the visibility of the interference, but we also heavily enhance the contrast, the amount of photons that we generate in the system. So we send in a pump laser, but now we can also send in a seed laser at the wavelength that we're going to illuminate the object at. And in doing so, we get stimulated down conversion in the crystal, and we generate way more photons at the 810 nanometers. So by having a much higher number of photons being generated, it's much quicker to form your image or to sense what's in one arm of the interferometer. And you've also enhanced the coherence length of the photons. If you use T2 CW lasers, then the generated light also picks up the mutual coherence of those two lasers. So now the alignment is much easier in the interferometer because you don't need to have them aligned to within a short coherence length that you might have from a spontaneous process. So in Bristol, we use this seeding technique in order to detect methane at 3.2 microns in an interferometer where we only ever detect 850 nanometer photons. So this could be tuned across different gases, but we chose to work down here around 3.2 microns with methane. Pump wavelength is around 671 nanometers. So this is like a red colored laser, cherry red colored laser. And this comes in and is combined with a 3.2 micron beam from a quantum cascade laser. These are combined on an off-axis parabolic mirror and focused into the nonlinear crystal. And in doing that, we generate a signal beam at 850 nanometers. All the beams are retro-reflected back to the off-axis parabolic mirror, while the idler beam passes through a gas sample, in this case methane, and the pump is reflected. The signal is also reflected, but actually we play a trick here. Earlier on, we were having to move one of the mirrors in the interferometer to change the phase, but that takes time, and it's also not necessarily repeatable, and it's also expensive to implement piezo control inside these systems. And so by tilting this one mirror in the interferometer, you can have the returning signal phase front be tilted with respect to the second generated photons on the second pass of the crystal. So if you have two beams that are one with a tilted phase front compared to the other, then you'll get a spatial interference on the camera. By looking at the visibility of the spatial interference, you can assess how much absorption the idler saw from the gap in the interferometer. So let me show you that working. So this is, it's hard to see with your lights here, but maybe, well, it's kind of good actually, because you can see some stripes here, but down here you can see that those stripes are suppressed. So what's happening is we're tuning our quantum cascade laser to be on resonance and off resonance with the gas. Thanks, that's perfect. And so these are the images that we'll pick up on the CMOS camera from the tilted fringes. When the laser is tuned off resonance, there's less absorption in the interferometer, so there's a high interference visibility. If we bin all the pixels of the camera, you can see this is the red curve here that has higher peaks here, so a larger visibility of the interference. If we tune the laser onto resonance with an absorption of the gas, so a vibrational resonance of the methane, then we see a suppression of those fringes. This black line is lower than the red line, the visibility is decreased, and we know that the gas is present. So this is just two wavelengths, but we can repeat this for many, many wavelengths across the methane absorption spectrum around 3.2 microns. And we see what is expected for methane, these strong kind of multi-Lorentzian dips that come from different vibrational modes of the methane. And this matches the high chance database calculation for the methane at the particular concentration that we had in the gas cell in the interferometer. Each point in this spectrum only took an exposure of 200 microseconds, so 0.2 milliseconds per image, and then you calculate the visibility as you go. We oversampled here, so really you could measure the spectrum in just a few seconds if you wanted to using this technique. Yeah, cool. Yeah, please interrupt.
Is there a risk of false positives and negatives with this process? What are the possible other cases of difference here?
Yeah, so I guess you have to be a bit careful that the interferometer is reasonably stable. Right? If it's shaking around or something like that, then that might wash out your visibility. But as long as it's stable over the measurement time, and they are for us, then that's okay. There are other gases around the place. However, this particular line of the methane is quite isolated from other gases, so that's good. Actually, that brings me on to this slide where actually water is often a problem when you're doing this kind of gas spectroscopy, because water is generally everywhere and has quite strong absorption. But as I mentioned, the methane sits slightly away from these very strong water absorptions in the lab. So actually now what's happened in this image here, so these may look kind of lower visibility than you saw before, and they are. And that's because we've not only taken the methane cell out of the interferometer, we've extended the length over which one arm of the interferometer propagates, the mid-infrared arm. It now goes 11 meters by bouncing back and forth across the table in the lab and bouncing all the way back in the interferometer. So actually now these methane lines are just from the background methane that you have in the lab. So we'll joke however many people, or if it's after lunch or something, will it be stronger? But yeah, this is just the background level, and it corresponds to a few parts per million of methane in the lab. If we tune the laser wavelength further, you see this very strong absorption, and that comes from water vapor in the lab. And the strength of this absorption agrees very well with just the humidity that we measure in the lab using a standard hygrometer. So this is quite nice. This work has been published and is out now. We've just recently extended this work to remove the mirror from the interferometer that sends back the light. So we replace the mirror with what we call a Lambertian target, so a diffuse reflector, with the idea that if we want to use this kind of process, this device, outside of the lab, it's unlikely that we've got mirrors everywhere we want to measure a methane leak or something. But it's quite likely that there's going to be a wall or a piece of metal or a leaf or a piece of glass or something behind it that we can reflect off of. So we replace the mirror in the mid-wave infrared arm with a piece of paper in this case, but we've used some other objects as well. And it turns out that we had to put some lenses in to be confocal with the position of this target. And we can change the position of one of the lenses to change how far we try to image in this system. One thing we did first was to just tilt this Lambertian target back and forth. And what we see is that you see a drop in visibility as you tilt it. But compared to when we have a mirror in the interferometer, if you tilt a mirror, then you completely divert the beam from going back through the crystal. But if you tilt the diffuse scatterer, it's scattering everywhere. So if I tilt it more, it's still scattering light back into the interferometer. I tilt it around. So I can actually, if I'm pointing across the room and hitting the wall like this with the laser, I would still get enough backscattered light for my interferometer to work. Whereas if there was a mirror there, the mirror would have to be perfectly aligned to send the light back through the interferometer. So I mentioned we also tried some different materials here. So this is with paper. We can still get high visibility for the kind of on-angle hitting of the paper. But we also tried glass and brushed metal. And you can still see the interference showing the methane spectrum across the lab. However, we also tried a leaf. It didn't work as well. So maybe we'll try out different kinds of leaves and see which one might give us the back reflection. But yeah, this is work towards kind of taking the device out of the lab. Okay, I want to switch gears a little bit and go through some of the cold molecule work now, which is using these two interference effects to investigate the coherence and coupling of organic molecules at low temperature to nanophotonic devices. Okay, so a little bit about the molecules that we work with. I already mentioned they have a singlet ground and singlet excited state and are coupled to a manifold of vibrations in the ground and excited state. The molecules we use tend to be, for this coherent applications, are polycyclic aromatic hydrocarbons. So these are molecules that are made of benzene rings, purely carbon and hydrogen. The simplest one, or one of the very simplest ones, is this anthracene molecule, 3 benzene rings fused together. It emits photons at around 400 nanometers, so blue kind of wavelengths. As you add more and more benzene rings on, you can shift the wavelength longer and longer. Pentacene is green, dibenzanthantrene is orange, so DBAT for short. Terylene is kind of pushing into the red. And as I mentioned earlier, dibenzoterylene, our favorite molecule, emits at around 780 to 795 nanometers. So these molecules are kind of overlaid with many of the other kind of photon sources or other qubit-based systems, including the kind of alkali earths, defects in diamond, alkali atoms I mentioned for quantum memories already, and quantum dots pushing towards the near-infrared. There's a question over whether we can push the size of the molecules large enough to generate photons at telecommunication bands. It's very difficult because the decay where you only emit vibrations of the molecule, so the molecule vibrates in order to decay from the excited state to the ground state, becomes far more probable with a much larger molecule. And when the energy gap gets too small. And so that means we haven't found a molecule that works out here, but we are working on similar systems that are being worked on here by our superhedrals group, so carbon-based defects in a silicon lattice where we can generate telecommunication band photons directly. I mentioned already that there's this excited state triplet in the molecule that has some splitting between the different triplet levels based on the spin of the electron. Those splittings tend to be at a few to 10 gigahertz regime. And so there's a possibility to interface these spin split triplets with microwave photons as well. So this molecule is quite small. It's only a couple of nanometers across in size. You can't just interrogate the molecule on its own. It'll tend to react with oxygen and photobleach, or it'll bend around, or it'll destroy itself. So in order to look at these molecules, we embed them in organic crystals that are made from other polycyclic aromatic hydrocarbons. We tend to embed them in a crystal where the host molecule, in this case anthracene, the 3 benzene rings I showed you on the last slide, has a much bigger band gap than the molecule you're embedding inside. That means that the molecule host, the crystal, is generally transparent at the wavelength of the emitter. So we can grow anthracene nanocrystals, a few hundred nanometers across, that contain of anthracene that contain a few of these dibenzotyrrolene molecules. We can also grow these molecules as a thin film, and we can also grow much bigger molecular crystals that you can really physically see, pick up, and put down again. Although here you can see we cracked this one when we picked it up with the tweezers, but this is fine because there's plenty of area which is very flat and optically clear. The transitions between the ground state and excited state stem from transitions between the highest occupied molecular orbital and lowest unoccupied molecular orbital of the molecule. It's exactly the energy that's lost when this decays that gives you back a single photon. This is around 785 nanometers for this DBT molecule. The molecule, when it's in its excited state, can also decay to one of the vibrational levels of the ground state, and it'll deliver a redshifted photon, and then it'll get rid of the rest of its energy in a picosecond timescale by vibration and put it back into the ground state, ready to be excited again. You can use this vibrational manifold in the excited state as a third energy level in your system in order to invert the population in the molecule. So by pumping at a shorter wavelength, a higher energy, up to one of these vibrational levels, you can have very fast non-radiative decay, again, giving away vibrations to the crystal that puts the electron into the excited state efficiently. So this means you can then get decay from that excited state, and it can give you this coherent transition that involves no vibrations. We call it the zero phonon line, as do people who work on these defects in diamond, or you can still get these redshifted fluorescence events. This is a confocal map. So this is scanning a laser just spatially across a crystal at room temperature. Each of these bumps is fluorescence from a single molecule. And we're also, you can also see the edge of the crystal here actually scattering light in this kind of ridge on the edge. This is at room temperature. We tend to cool these crystals down then to cryogenic temperature using a closed cycle cryostat, like this Montana cryostation is one of the systems we have. When we go from room temperature, where we can see many, many molecules, we get to low temperature and we can only see one molecule in the scan. But that's not because all the other molecules have disappeared. It's the fact that at low temperature, all of the molecule transitions stop interacting with phonons and get very narrow band. So our single frequency laser is now only resonant with one of the molecules in the ensemble. If we park our laser at one spot and we have a high doping density in the crystal, then as we tune our laser wavelength, we're able to see many molecules come into resonance with the laser. And so this is just a zoom in of the spectrum. So each of these sharp lines is one single zero phonon line of a single molecule. The difference in them comes from local stress, local strain in the crystal that just shifts the energy gap very slightly between the ground and excited states. But this is useful because now we can spectrally select a single molecule out of the system rather than only spatially selecting it. As we cool down from, say, 40 Kelvin to 30 to 20, you can see that as we scan our laser across just one of these molecules, you can see that the line gets extremely narrow and it gets all the way down to the Fourier limit. So around a 40 megahertz line width for a 4 nanosecond excited state lifetime means that the photons being emitted should be fully coherent, fully lifetime limited, Fourier limited. If we disperse the fluorescence from the molecule in a spectrometer, then we're able to observe the zero phonon line in the spectrum. It's around 50% probability that it decays that way. The rest of the time it decays to that vibrational manifold of the ground state, giving a redshifted photon. So that's what these small spikes are here in the carrier spectrum. Discrete vibrational modes. We're able to send photons from the molecule to a 50-50 beam splitter. And the reason we would do that is we want to check whether it was really a single molecule and whether it's really emitting single photons. If it's emitting single photons, then the photon has to choose to go to the top or bottom output of this beam splitter here. And if we put detectors at those two outputs, if the photon chooses to go one way or the other each time, then we're only ever going to detect one photon at one output or the other. We'll never see coincident events between the two outputs. This is what's called measuring the second order correlation function. Some people call this measuring anti-bunching. So what's plotted here is the time delay between detections at the two outputs of the beam splitter, and you can see at zero time delay, you've got a strong suppression of the second order correlation function, a strong suppression of the coincidences at the output of this beam splitter. So this is what some people call anti-bunching. It proves that we have a single photon source. But as you increase the illumination power, you see you get these oscillations in the system. So the oscillations, you can understand, come from Rabi oscillations between the ground and excited state. Why do they show up in this second order correlation function? Well, when I detect one photon at the output, this sets me at time zero. At time 0, I detected a photon, and I know I'm in the ground state because I just detected a photon. I project myself into the ground state. Now, if I see another photon at a later time on the other output of the beam splitter, it means my molecule must have entered the excited state and decayed. That means that this measurement is a probe of the excited state population in the molecule varying in time. So that's why each side of this, you see these oscillations. These are Rabi oscillations between the ground and excited state, and the black lines on these plots are solutions of the optical block equations. So it's a two-level system. So this is very much agrees with theory. If we increase the temperature of the cryostat, we increase the dephasing rate with respect to the spontaneous decay rate in the system. Then we're able to see a suppression of these Rabi oscillations until they've gone away, because there's no coherence left between the ground and excited state when you increase the temperature. There's also a pulling away from 0 here, and so it doesn't look as well anti-bunched here, but actually that's just because our detectors aren't fast enough to measure this dip that should look like a sharp point going to the bottom here now in the fully dephased regime. There's more details about that in the paper here. Just then, we were sending one photon into one input port of the beam splitter. But as you may know, if you send photons into 2 ports of a 50-50 beam splitter, if those 2 photons are completely indistinguishable from one another, they'll undergo quantum interference, 2-photon interference. They'll both bunch together such that both photons go to the top or both photons go to the bottom. This is what some people call Hong-Amanda type interference. If we monitor have detectors at these 2 outputs, we should see no coincident clicks if the photons are indistinguishable from one another because they're both bunching together to top or bottom. So that means if we make our photons parallel polarization at the input, then we should see a suppression of a central peak in the second-order correlation function. This is for pulsed excitation. And if we make the photons perpendicular to one another, then we should see a revival of the central peak, because now the photons can go one up, one down, or one down, one up. We can calculate the indistinguishability of the photons that are generated by integrating that central peak in the cross and co-polarized case and calculate that. And it turns out it depends on the modal overlap of the photons and the ratio of the dephasing rate and the population decay rate in the system, twice the dephasing. In the Fourier limit, this goes to 1. And in the perfect match case, this goes to 1 as well. So if we vary the dephasing rate by changing the temperature of the molecule, then we're able to see that we revive this peak, but it has a little notch out the middle. And then the width of that notch corresponds to the coherence time of the molecule. As you increase the temperature, the coherence time shrinks, that gets narrower until it completely disappears, and then you have incoherent photons. Similarly, with this modal overlap, it's just a monotonic increase as you change, say, the polarization of the 2 photons until they're completely mismatched to one another. Or it could be the time of arrival or the spatial mode that they're in. We can also do the same thing with continuous wave excitation in the system. In a continuous wave case, we start off with a dip that goes to 0. The 0 dip means both photons are either top or either bottom. If we go to the cross-polarized case, the second-order correlation function goes to 0.5 because we now have the option of 1 photon down, 1 photon up, 1 up, 1 down. So similar to the before, but it's just kind of the picture looks flipped. If we change the dephasing rate, again, we can see that the central dip narrows down, but actually it always goes to 0 at 0 time delay. So some people assess the coherence of their photons by only looking at 0 time delay, the visibility of this dip. But it turns out the visibility of this dip, if your detectors are fast enough, will always be 100%. So a bit cheeky, but you can actually assess the full photon wave packet indistinguishability by integrating these second-order correlation functions. Now, here you can't just integrate these directly because they would blow up, because they're 1 everywhere else, so they're diverging integrals. But you can do 1 minus the second-order correlation function combined in this way, and what you'll find is a similar term to before, this modal overlap. But now the secondary term has a saturation parameter in here. This is how strongly you're pumping the molecule. So it turns out to measure the indistinguishability, you need to use 2 different powers to extract the 2 parts to this equation. So we went ahead and did this. We took a single molecule in a nanocrystal, cooled it down to low temperature, excited it continuously or with a pulse, and then used an unbalanced Mach-Zehnder interferometer to interfere photons at this final beam splitter. How does that work? If the first photon takes this delay line, it'll arrive at this beam splitter, And during the time whilst the first photon's delayed, another photon's generated and takes the bottom path of this unbalanced Mach-Zehnder interferometer. That means that then the photons can arrive simultaneously at this beam splitter and be detected at the outputs with avalanche photodiodes, silicon spats. This is an example of when the photons are co-polarized with one another, parallel polarization. You can see the interference. And when we make them cross-polarized for continuous wave pumping, you can see we suppress that central dip, so the dip goes away. We can do similar for pulsed excitation. However, here you can see our pulses are not quite as well separated as I showed you earlier. We should have used a lower repetition rate laser, but we had our Thai sapphire working with the normal 80 megahertz rep rate, and we chose to use that in this case. But by fitting, you can still see that the central peak has been suppressed between these two pictures. So what about having to measure two different powers in order to assess the indistinguishability from this continuous wave case? We measured at two different saturation parameters, fitted the curve, and it agreed with the pulsed case, an indistinguishability of around 0.5. The indistinguishability was not perfect here, and that's because the temperature of our cryostat was around 5 Kelvin for these experiments. And so we've just got a new cryostat from ICE Oxford that's now going to get us to colder temperatures and be able to measure a higher indistinguishability. So I didn't quite get to the final part for this waveguide part, but I don't know if we've got time for me to through. It's bang on the hour now.
Oh yeah, you can go like that.
Okay, right. So the Berkeley late start allows me a Berkeley late ending as well. And it's the end of the day, right? I know people have got to watch the NBA finals or something too, but, you know. I'll have you out of here on time, no worries. I want to see it too. Okay, so let's look at these molecules and coupling them to nanophotonic structures quickly. So we've been working on coupling molecules to solid immersion lenses and nanophotonic bullseye gratings. This is just to enhance the directionality of the emission. It's not coupling directly to like a guided optical mode, but it allows you to collect more photons. And we've got this nanowire waveguide case that I'm going to talk more about shortly. We've also coupled to what we call hybrid plasmonic waveguides, so metal islands on the top surface of a photonic chip, where molecules that sit at the center of a small gap are coupled to a propagating plasmonic mode. And we've also been developing integrated nanobeam cavities in order to enhance not only enhance the directionality of the emission of the molecule, but also spectrally enhance the decay on that zero phonon line that I mentioned earlier. We're also using, so these are nanophotonic cavities, but we're also looking at optical microcavities, including tunable cavities where we have two mirrors that can be independently moved from one another, and also monolithic vertically emitting cavities where we can introduce molecules between two distributed Bragg reflectors. So let's concentrate a bit on the waveguide coupling case. If I have a dipole and it sits between two nanophotonic waveguides, the closer I put those two waveguides to the dipole, the more and more light I can couple from a single molecule. So these are FDTD simulations in a very idealized picture, but it shows you that you can push the coupling efficiency to the waveguide up to tens of percent. So we wanted to demonstrate this experimentally, and so we went ahead and designed some silicon nitride nanophotonic waveguides that have a small gap between the waveguides in the center, focusing grating couplers to bring light in and out of the nanophotonic device, and then a microcapillary that allows us to introduce a molten mixture of molecules inside the gap between the two waveguides and freeze them in place. So these are the nanophotonic waveguides fabricated by Wolfram Pernice's group, which at the time was at the University of Münster. He's recently moved to Heidelberg. Here you can see you've got the focusing grating couplers and the waveguides. Zooming in on the center, we can see a small gap, a couple hundred nanometers generally in width, although we had varying gaps on different waveguides on the device. Focusing grating couplers, and the grating couplers had an emission-shaped spot size that was matched to our confocal microscope so that it could be mode matched to optical fiber. So that's the silicon nitride nanophotonic waveguides, but what about the capillaries? To make the capillaries, we lay down a polymer on the top surface of the device, and we overcoat that with silica just by depositing sputtering glass on top of the polymer. By then heating the whole thing up to a high temperature in air, around 500 degrees C, then you're able to burn out the polymer from underneath the silica, leaving yourself an open capillary. You can then flip that over, put it onto a hot plate, and introduce a molten mixture of anthracene and DBT that then gets sucked into the chip by capillary forces. That happens at about 200 degrees, the melting point of anthracene. And so then when you take that off from the hot plate, it cools down quickly, the anthracene crystallizes in the capillaries, and then you can wash away the excess anthracene from the top surface using toluene. So this is an example of a capillary, no waveguide at the moment. And here you can see if we put our laser into the center here and scan the wavelength of the laser, we're able to see dibenzopyrrolene emission or zero phonon line resonances inside the capillary. Around 100 megahertz line width. So about twice the Fourier limit, but in this case, this is probably due to the temperature of the cryostat rather than from the molecules dephased through other means. So then we need to characterize how the molecules coupled to the nanophotonic structure, and I mentioned we do that by a resonant Rayleigh scattering interference in the output waveguide. How does this work? I mentioned already. So the laser comes in. It has, depending on the coupling efficiency, the laser either couples to the molecule or not. The laser enters the output waveguide, but so do photons that are scattered by the molecule without it entering its excited state. These photons have the same line width and wavelength as the laser, and therefore they're able to interfere with the laser, but only the strength of the interference, as you can see, depends on how many of those photons are scattered into the output waveguide, and that depends on the coupling efficiency of the molecule to the waveguide. So let's ignore the equations because we don't have enough time to go through them, but this is an asymmetric structure. If we had a perfectly symmetric structure and the molecule sat in the middle, then the phase shift of the scattered light compared to the laser light that enters the waveguide is 90 degrees, and that results in a completely Lorentzian interference line shape in the output grating coupler. If the molecule is sat somewhere else, and it doesn't pick up a symmetric 90-degree phase shift, then you'll see a phanotype line shape in the output, and that will depend on the phase shift that the light picks up compared to the laser light. So here's the full experiment. We had the waveguides crossed by the capillaries. The capillaries are tapered across the waveguide only in the center. We're able to fill those with the anthracene, freeze the anthracene in place. Put the whole thing in the cryostat, and we can see lots of redshifted emission when we look at the photons. And then if we zoom in on the blue curve, then we can see dips arising from this interference effect in the output. The dips don't agree with a 90-degree phase shift. They agree better with a 62-degree phase shift after the fitting. And this says the molecule's not sat perfectly symmetrically in the system. Now, that's not a problem as such. It's just an interesting fact that it can sit at different points in the gap and couple differently. The coupling efficiency in this case was around 10% to the optical waveguide, so not perfect, so we can do better. And the visibility of this interference also depends on the temperature of the cryostat. So a colder cryostat will give a higher visibility as well. If you illuminate the system more strongly, pump more power into the optical waveguide, you can saturate the system, and then you go away from this resonant Rayleigh scattering regime into exciting the molecule properly, and this means that this interference effect goes away. So you can kill this interference effect by turning up the power, and you'll also power broaden the Lorentzian line that you measure from the molecule at the same time. In order to enhance the efficiency of the coupling to the nanophotonic device, you can introduce a cavity into the system, and this will, for a reasonably modest cavity, it will enhance the efficiency of this process to close to 90%. So I also mentioned these vertical defect cavities that we're working on, but I won't go too much into that. We're using the same reservoir filling effect, but now the reservoir is between two Fabry-Perot. It builds a Fabry-Perot cavity between two DBRs. One of them slightly curved, so it's focusing, and this means you can get a very well confined optical mode. And these are currently being fabricated in our clean room in Bristol. All right, to wrap up, there's some references for this molecule work, but instead of reading all those references, you might just want to take a look at this review article from a few years ago now that I wrote with a colleague in Italy, Costanza Toninelli, and other colleagues around Europe. This goes into quite some details about the different uses of these molecules in photonic and quantum technology. As an advert, there's an open position in my group to work on networked quantum memories. So using these molecules and interfacing them with rubidium memories. If you're interested, please let me know, or send the advert to people you know that might be interested to move to the UK. And with that, I'll thank the whole team and all the funders, and thank you very much for listening.